So this video is brought to you by Lego Town Overall Sky. So we're going to solve a system of equations using a matrix. And essentially we're going to do these row equivalent operations. And there's a whole big theory behind this. You can take linear algebra. There's two versions of it. There's the there's two undergrad levels, and I'm taking a grad level one. It's quite exciting. Anyway, matrices is a plural of matrix. Essentially what we do is we take this linear system and we rewrite it in the following ways. Note, an entire equation becomes a row, and then the columns are corresponding to the different parts of the equation. For example, the 2 and the 1 are the coefficients of a column of x's. The negative 3 and the 4 are coefficient of the column of y's, and then these are like the solutions, or what the equation is equal to. So each row represents an equation. Each column represents a set of variables or coefficients. Let's just call those coefficients. And a vertical line represents a diagonal, is what that is. The vertical line represents the equal sign. My bad. So we call that equation an augmented matrix because it contains the coefficients and also the constant terms. These are actually the constant terms. So some other jargon you should know: a matrix that is m by n has, I did this wrong, m rows and n columns. This matrix, when you have the same number of rows and columns, you call it an n by n, or a square matrix. So this particular matrix happens to be a 2 by 2 matrix. 2 rows, 2 columns. The intersection of a row and a column, for example, this is a number, also known as an index. And then the main diagonal, which would be this, of a square matrix goes from the top to the bottom. Okay, so let's apply this to a 3-variable linear system. So ignore this for a second. Here is the original Gaussian elimination, where our goal was to get an equation in this form, and then we back substituted the value for z, and then that gave us y, and then we put both those in and we got x. So the matrix of that form would look like this. Notice we have a, b, and c equals d. That's the first equation, and then we're plugging in zeros for all the missing terms. So one of our goals then is to do these operations on a matrix to get it in that form. Zeros in this position. So we're going to take this system and rewrite it in that augmented matrix form. Notice I put the 2, the -1, the 4, and then the -3, and blah blah blah. So each row is an equation. We can always do these 3 things to those equations. There's a whole theorem and proofs of why these are all work. They're actually called elementary row operations. Interestingly enough, you can do it to columns as well. So we can interchange rows, we can multiply by a value, and we can add the rows together. Very similar. It's essentially the same thing we're doing in Gaussian elimination. So here you're told to do all of these. And then you're going to get a nice equation that you're going to see on the next page. So you could try this on a separate sheet of paper and see how it works. Let me just do one of them. We're going to do a new row 2. It said interchange rows 1 and 2, and then do new row 2, which equals -2 times row 1 plus row 2. So I'm going to do these 2 things in one step. I'll interchange. So this is actually the row 2, the first row, had we done that first. So we're going to do -2 times this row, which I'm calling row 2, plus row 1. So if you see what happens, what we're doing is we're eliminating this first variable, because -2 times this is -2, and -2 plus 2 is 0. So remember, we interchange the rows, so we put this row first. 1, -2, -10, shoop, this thing, and then -6. The bottom row we're leaving unaffected. And then what we're doing is multiplying -2 times this and adding it to that, and that's going to become, I forgot to put the little arrow, that's going to become the new row 2. So -2 times 2 is 2, -2 plus 2 is 0. -2 times -2 is 4. 4 plus -1 is 3. -2 times -10 is 20. 20 plus 4 is 24. And then -2 times -6 is a positive 12. So there I've done these first two. We're then going to do 1/3 now times this row 2. And if you look at that, I might as well just do that one real quick. 1/3 row 2 leads us row 2. You can see this is a little tedious if you're writing out all your steps because there's a lot of writing to do. So 1/3 times 3 is 3. What? 1/3 times 3 is 1. 1/3 times 24 is 8. 1/3 times 12 is 4. So we've just made the numbers smaller. They had a common factor of 3. We essentially divided out 3. So I've done row 3. I'll leave 4 and 5 as something for you to do. When you get to the next page, you're going to see exactly what this is supposed to look like. In the end, we get zeros in this area, ones along this area, and now we know that z is equal to 1/2. Try again, -1/2. So we can go back with Gaussian elimination and we can say, oh, well, this equation tells us that y plus 1 times y plus 8 times z, which in this case happens to be -1/2, equals 3. And continuing along that pattern, let's see, 8 times -1/2 is -4. Add 4 to both sides, and we get y equals 7. Wonderful. And then finally, we can plug both of those into this top equation, and here we have x plus 7. Times -2. Okay, so the 7 should probably come after the -2 for clarity, because that is the y value, and then plus -10 times the z value, which is -1/2, and that is all to equal -6. While solving that, here we get -14 and +5, so -14 and 5 is 9. -9, add that to both sides, and we get a +3. So there's the ordered triplet, which is the solution to that equation. So that row echelon form, which is what we call this, means we're able to use back substitution and get this, because we have ones on the diagonals. So we know the very last row gives us one of the solutions. But there's an even better one and an even simpler matrix where we could have continued those row operations to get ones, only ones along the diagonals. This is reduced row echelon form, RRF. And here it very clearly shows us that x equals that 3, y equals the 7, and z equals that -1/2. Now the work to get there, we haven't shown here. That might be a fun exercise for you to try out. How could you add and subtract these things to get zeros on those diagonals? You have to multiply by some stuff and keep working. What's really nice is the calculator will do all of this for us. Now, I happen to be a big fan of Desmos. Many of the instructors at Jackson College are big fans of Desmos, and I haven't looked to see if we can do this in Desmos, so maybe I should have done that before I made this video, but whatever, it's quite easily done in our calculator. So I'm gonna end this video.